So we know that one of the main ways that we can reduce the number of dimensions in our data set is through using principal component analysis, or what we call PCA. Many times we're not going to have data sets that have very few dimensions. There's going to be many dimensions in our data set pretty often. And in order to capture a lot of the information, in order to capture a lot of the variance in our data set, while making sure that we're able to process this data through having fewer dimensions, we're able to use PCA, converting the larger dimensional data set into the smaller two, three, four-dimensional data set that we're able to process better. And there's many different applications of PCA. First is just visualization. If you have many different features in your data set, you're able to use PCA to condense those to the two, three principal components, and you're able to visualize those through a 2D or 3D PCA plot. So comes in handy when you're trying to visualize the variance in your data and you have a lot of different features. You're able to visualize those by converting them to principal components. Now, when we talk about principal components, these you can think they're essentially you're projecting the data set onto a new set of axes, and then you're transforming the original data onto those axes. So, for example, if you have 30 features in your data set, which two axes that can we create that are A or uncorrelated to one another, orthogonal to one another, and can capture a large variance of the 30 features. So that's what we refer to as our principal components. These are the new axes that our projected data set will have. And once we have these axes, we're able to take the original data set, we're able to project it onto the original axis. And so that's how we're able to do PCA, condense the number of features in our data set so that we're able to have fewer features, but we're also able to maximize the amount of information that we're capturing it within the data set. So that's the first. Visualization helps us with visualizing the data. Second is PCA is incredibly useful for handling multicollinearity. When we have many different features that are collinear, right? That exhibit multicollinearity in a sense that they're strongly related to one another. They have this very strong correlation. We don't want to use those features into our model because those are going to be redundant features. It's going to provide some extra noise in the model. So, how can we create independent features from this large feature space? Well, we can use PCA to convert those into principal components. And the thing about principal components is that every single principal component is going to be uncorrelated to the other principal components. Right? If we take the dot product of principal component 1 with principal component 2, we will get 0 because they are two independent vectors. They are two independent principal components. And that's one of the features and one of the main things about PCA is that when you create new principal components, they're uncorrelated and that they're independent. So they really can help us resolve this problem of multicollinearity when you have multiple features that are related to each other in a data set. Now, how does PCA work? First, we take the eigenvectors of the covariance matrix. So the covariance matrix is a representation of the relationship or the covariance between two features. When we take the eigenvectors of those, this is relating what scalar multiplication of the eigenvector. So if we have an eigenvector here, what scalar multiplication do we need to apply to this eigenvector such that when we have the exact same when we have a matrix and we multiply it by this vector, we get the exact same transformation. So by applying this matrix to this eigenvector, that gives us the same transformation as applying the eigenvalue to the eigenvector, right? The only change is in the magnitude. The direction does not change. And so that's one of the features about eigenvectors. You multiply an eigenvalue by an eigenvector that is equivalent to matrix transformation on that eigenvector. So that's one of the beauties about eigenvectors. Now these eigenvectors are actually, once you normalize them, they're actually the principal components of the new feature space Now, the principal component with the highest eigenvalue is PC1, and that will contain a majority of the variance from the dataset. PC2 is going to contain the second highest eigenvalue, and that is going to explain the second highest variance in the dataset. And then it will diminish as you get more principal components. But this is the essence of PCA. We're able to extract these features or independent principal components to maximize the variance that we're capturing in our data while also minimizing the number of features that we're using to capture that variance. And so that's PCA is incredibly useful for this. One of the other things that is important to know is that these two, PC1 and PC2, are obviously uncorrelated, and the sum of the squares of the values in a loading for a specific PC is equal to 1. So what does this mean? So when we have PC1, that is equal to some linear combination of the features. Right? It is equal to some linear combination of the features. Now, the weights in this linear combinations are what we call the loadings. And the sum of the squares of these loadings will always equal 1. Same thing with PC2. It is going to be a different linear combination, still independent from PC1, a different linear combination of the feature space where the weights are considered the loadings, and the sum of the squares of those loadings are equal to 1. And so that is PCA in a nutshell. If we also think about how can we extend, how can we make things more creative, and that is due to conversion to Leetcode questions or conversion to programming questions, is when you're converting these concepts that you encounter in your everyday life and convert them into a problem that you can actually solve. It engages your creativity, it makes your mind more stimulated, and it offers a new paradigm to really shape how you think about things in your frame of reference. So when we think about formulaic versus manual processes, right? This is a perspective that could be had on whether you want to have something formulaic or manual. And now when we think of formulaic, you could also think of this as programmatically. Do you want to do something programmatically that has a structure, that has an algorithm, and that's automated, or do you want to do something manually? Well, we can shift the perspective on this and think about a word search. We can think about in a word search, the problem could be we are trying to find this specific 3-letter word, for example, trying to find this specific 3-letter word in this word search. So we know that that 3-letter word is right over here. Now there's 2 different approaches that we can take to actually get to this 3-letter word. We have the formulaic, the programmatically, or the automated, or the more efficient way of doing and finding this word, or we have the more manual process whose runtime is going to be higher. Now, what is the formulaic or programmatically way to do this? Well, what we can do is we can essentially take every single letter that we are at. We can see, does this match the first letter in the word that we're trying to match. If it does, then we see, can we get it to the next letter by either going up, down, to the left or to the right, right? Given that it's in bounds. Right, so if we write the pseudocode for this, so it's if the first letter matches, right? And then while we can get to the next letter by one of up, down, left, right, and it's in bounds, and it's in bounds, right? Then we're going to increase our counter by one. And if our counter, right, equals the length of what we're looking for, then we're done, right? We found it. Then we can return the indices. So this is what we would refer to as a more programmatically way to do this, to do this. A manual way of doing this would be to capture every single combination first. So every single combination in this word search we would gather and we would check if that word that we're looking for is in this word search. So what would this look like? We would first start with, okay, ARJH is one combination, or ARJ is a combination, ARJ is a combination. ARF is a combination. ABC is a combination. So we would need to create a methodology to create these different combinations. Now, how are we able to create these different combinations? Well, those come from the idea that you can either go left, up, down, or right, right? If you're starting at A, you can either go, you can go to the right. When you're at to the right, you can either go to the right again, or you can go down, or you can go down. And so you can think of this almost as a graph problem when you're trying to list out all of the different paths in the graph, right? So you can think of this as a graph problem or backtracking for a problem. You're trying to list out all of the paths, all the paths. Reminds me of DFS, where you're going all the way down one path and then going immediately back and then going down to another path, immediately back, one step back, another step back, doing that again. It sort of reminds me of DFS or backtracking. So that's how we can do this sort of the manual way or through combinations. So that's what we wanted to go over today, went over PCA, went over how you can extend the idea of having something formulaic or hard coded as a concept to converting it to a word search programming question. So that's all for today. I'll see you in the next video.